All right, so in this lecture, we're going to study the commutator again, but we're going to talk about it in the context of curved spacetime. This is going to be very familiar, and it's not a real critical step in our understanding, but I like doing it because these are the level of details that I think make a big difference. In curved spacetime, we can no longer think of this vector field as, say, a displacement vector field like we did in the previous lecture, where we took the point P0 and we connected it to the point P1 with a vector which represented the difference in the coordinates between the 2 points. Now we have to work a little differently, and the method we're going to follow is from Meissner, Thorne, and Wheeler's gravitation. I mean, that's where I learned this, and I'm basically going to represent it here. In my volume, I think there's only one volume of this book, we're talking about page 237. Now, the exposition I'm going to do here is not precisely the same. Otherwise, you could just go to the book. It's going to be basically the same, but I'm going to sort of flesh out some of the details. But we begin with, since in curved spacetime, you can't actually connect points with vectors because vectors exist in tangent spaces that live at points only in spacetime. Technically, that's true of flat spacetime too, but you can create the sort of convenient fiction that the tangent space and the underlying space are the same in a flat spacetime. In curved spacetime, we really can't do that. On the other hand, even in a curved spacetime, you can compress this to such a small region that you can treat it as flat, which is why the flat presentation is useful. If you think of this in a limit where this little object here gets smaller and smaller around this point, then it's going to become more and more of a true rectangle, and P4 and P3 are going to merge. And so the flat space explanation works well because we're always assuming, because that's an assumption of the theory. It's a part of the theory that we're dealing with a four-dimensional manifold, which of course is flat in a small enough region. But even without appealing to being flat in a small region, you can still do some pretty serious work. It just covers a lot more ground, and we're going to be covering that ground now and reviewing some as well. So I'll begin by sort of reviewing what we mean by vectors in an arbitrary coordinate system in even curved spacetime. We treat vectors in the spacetime as a way of understanding how curves in the spacetime are laid out. If I considered this vector field, this blue vector field, I'll call it x, and the green vector field we'll call y, and we know that x is a function on the spacetime, so I'll put a little x there. So x is a function on the spacetime, meaning, and what that really translates to is that the components of x, partial alpha, are a function on the spacetime. And so if I go to P0, I could now find the components of this vector field at the point P0, and those components are functions of spacetime. Now, once I have a well-behaved vector field, or even reasonably behaved vector field, I can create these lines which are the congruences, a congruence of lines in spacetime, whereby the vector field is tangent at all points to this line. And in this case, I'm going to call that line, I'll draw it out here in red. That line is a curve in spacetime, and everywhere along that curve, the tangent vector is given by this vector field. So I start with a vector field, and then I create that line. Now you can always do this, and of course there's all kinds of fascinating theorems about this, but these lines will generally speaking, not intersect, and if they do, it'll be in ways that are very specific and easy to understand. But we'll be dealing with regions of spacetime where these lines don't intersect, and of course there's an infinite number of them to fill all of spacetime. You could fill all of spacetime with these lines. And the one that I'm most interested in this particular, for this exposition, is this first one here, and I'll give it a name. I'll call it S. And S is, being a curve in space-time, every point on S has coordinates, and it's a function of a single variable, the parameter. And that's a parameterized line in space-time. And I could say that this point is set where sigma equals 0, the parameter equals 0, and I could say that sigma equals 1 at this point, but all the points in between have these different sigma values. And choosing 1 for this one is sort of arbitrary right now because the line can be reparameterized different ways. But we just understand that for this S curve, it's parameterized by sigma. Now, obviously there's a problem because, there's a complication because this other one, I would have to give it another name. So I could call it R, and it could also be parameterized by the same parameter. So I could choose a parameter value, sigma equals 0, and say, okay, that's P2. And then for sigma equals, say, 0.4, I would find some point over here where it's 0.4. This point here is given by S mu 0.4, and that's a set of 4 points. X0, X1, X2, and X3, all for this point right here, which I guess I'll call 0.5, all at 0.5. Or that's basically the set of pairs S0, 0.4, S1, 0.4, S2, 0.4, S3, 0.4, right? That's what these points are. So, but the problem is I could call this guy R, but as I said, there's an infinite number of these. So what we ultimately need to do is we need to introduce another parameter that tells me which of these curves I'm on. Am I on this one, this one, this one? And since there's an uncountably infinite number of such curves, I need another real parameter. So to really nail down which curve I'm talking about when I'm relating to an entire vector field, I actually need another real number along with the parameter to sort of tell us which curve this is. And then I could say this curve here, I could say the curve I'm particularly interested right now is actually given by S mu 0 sigma. It's the 0 valued curve for kappa. And this one here, R, might actually equal, it would really be S mu, say, 1.3 of sigma. That there's some other curve there that's given by the parameter kappa equals 1.3. We're not going to need that too much for this lecture, but this idea of having another parameter to tell us which of these curves of the congruence we're actually on, that does become important when we talk about geodesic deviation. And we'll be talking about that in in an upcoming lecture, because geodesic deviation is another characteristic that's real, or another another topic that has to do with the Riemann tensor, right? And it's another way of defining the Riemann tensor. Okay, so where are we? We've got so far the vector field x and y, and we have this one curve that's going to be, for right now, we'll just call it S mu of sigma. So now just the short version of how we understand vectors in space-time. And this is just the short version of something that we did a lot in the What is a Manifold lecture. But we're going to construct, I'm going to quickly review how we understand vectors in terms of these curves. But once you have a curve like this is a curve in space-time that's a function of a single variable, really. So you can always think of, now we imagine that we take a general function on the space-time, f. It could be it's just a function of the space-time, and it gives a real number. So you put in a point and you get a real number out. And of course this really means x of f of 0, x1, x2, and x3. So it's really a function of 4 variables, right? Or each coordinate in our space-time. But now, and sometimes people write it like this, but I don't like doing that because I don't like that index. That index really is meant to substitute x0, x1, x2, or x3. So to me, that this means I'm substituting one of those 3 in there. So that could be, for example, a function of x0. But that's not what we really mean by that. What we really mean by that is this. It's a function of all 4 of those things. And I think that's better exemplified by this process, by this notation. So our next step to understanding this function is we substitute in it, we substitute for each of these, we substitute the curve equivalent, right? That would be S0, comma, S1, sigma, S2, sigma, and S3, like this. And so now what we've done, let me erase that 0, it looks like hell. So now what we've done is we've inserted in each of these coordinate slots, we've inserted just the coordinate of the curve at a point sigma. So this is still a point in spacetime for a value sigma, a particular value of sigma, and we get the 0, 1, 2, 3 coordinates. So we're somewhere along this curve. Well, we're at the sigma point. Wherever the sigma value is, that's where we are. So, I could substitute S0 of sigma's 0.3 and S1 0.3. I could put all those values in here, right? These guys correspond to those guys. But once I've done that, then I realize, well, wait a minute. F is a real valued function. It's just a single number. So what I've really done is I've created f as a function of sigma. So I've taken 4 variables and I've collapsed it into 1. And the price I've paid, of course, is that I'm on a one-dimensional line, right? I'm on this curve. So this function here is only valid for the particular curve I'm dealing with. But since I've crammed it all into a single curve, I've got it as a one-dimensional function. And the reason that's important is because now I can think of the derivative of f with respect to theta as long as I'm on a certain curve S. And once I do that, I can use the chain rule to get an expression for this derivative. And the first step of that chain rule is right here. We just take the derivative, the partial derivative of the function with respect to x mu, and we sum it. We do the Einstein sum here, and then we get the function x mu with respect to sigma, which is what this is going to end up being, right? Because what we've done is we've turned x0 into a function of theta just by replacing it with this. So we end up, in a sense, renaming the function a little bit. But this we can calculate. We can calculate this. This is totally known. I'll put a little green circle around it. Because given the vector field x, we know we can calculate this curve. The method of calculating that curve is the solution of first-order partial differential equation. It's called the method of characteristics. I have not done a lecture on it, but it's actually a pretty interesting procedure that not everybody learns. We learn to solve partial differential equations in physics, but the classic ones, right? We don't do a pure course in just doing it. And I don't think there are any classic first-order partial linear differential equations. And the method of characteristics sometimes slips under the radar in our education. I might do a lecture on it. It's not totally easy, but it's not super hard either. But anyway, the point is given the vector field, you know the equation for this curve. Given the equation for that curve, you can take this derivative, right? This derivative would literally be partial s mu partial sigma. Remember, the s has suddenly got replaced by x because of this connection here. A little bit of another notational trickery that becomes a bit confusing if you don't track it carefully. But then the next step is to take this guy and write it this way. Partial x mu partial sigma partial x mu, and then you pull this arbitrary function f out. And once you realize that's an arbitrary function, you can then define the sigma derivative of an arbitrary function as partial x mu partial sigma partial mu. We'll use that sigma partial mu. And this guy here actually becomes the vector field of tangency to the curve, and this is the specific curve S. So basically we've defined a vector field in terms of a single curve that goes through, say, this point P0. So if I wanted to do this at P0, remember this is going to still be a function on the space-time, right? Everything's a function on the space-time. And Where's my little x in there? And so to build up the entire vector space at P0, we just have to talk about every conceivable curve that might go through this point. And every conceivable curve will have a tangent vector at that point, and the set of all those possible tangent vectors is the vector space at P0. And notice that the basis is given by this guy, which is directly traceable to the coordinates of the spacetime, and that's why it's called the coordinate basis. Now, this is a review, right? This is a quick review of something we covered in detail in the what is a manifold section. And but this is actually the technically, I mean, it's a quick review, but it's pretty comprehensive. So anyway, the point is that that's how we define our vector fields. So with that review in mind, now we're going to attack this question of the commutator. And the reason that place is a good place to start is we need to talk again about an arbitrary function on the spacetime. This is a typical theme. This theme shows up whenever you talk about vector fields. Because they're operators, you very frequently introduce arbitrary functions on the entire spacetime in order to talk about the operations of these guys. So that's what we're doing here. We introduce another function on the spacetime, and we're going to ask ourselves the question, what is the difference in value between f at the point 4 minus f at the point 3? And can we figure out what this difference is just using information local to the point P0? And what are we given? We're given the vector field x, and we're given the vector field y. So when we say we're talking about things local at P0, we really want everything in terms of the vector field and its derivatives at P0 of x and y. And then that has to tell us the difference in this function. I can no longer ask really what's the difference in the coordinates, what's this little vector connecting them, because we're talking about curved space. So we can no longer just treat these vectors x and y as displacement vectors, as I've said. So we'll begin by asking ourselves a slightly simpler question, which is, what is the value of f at P1? And we'll use Taylor's theorem, just a simple Taylor expansion to go from linear, to go from P0 to P1 for f. So the value of f at P1 is clearly the value of f at P0. And when I have no argument with f or with a vector field, or when an argument is missing, then you know it's P0, right? P0 is the sort of the base point of all of our analysis. So I don't have to write f of P0. I just leave that off. So it's equal to the value of f plus it's going to be the derivative of f with respect to the coordinates times this vector field, this gradient vector field. In this case it would be it'd be x, because we'll put some tangent vector here, and that'll be x at P0, which under my convention would just be called x because it's at P0. So this is little x, right, representing a space-time coordinate, and then this is capital X, mu. But we know that capital X mu is really this curve. It's a tangent vector to this curve, and that curve is part of the congruence of curves defined by x. So when I think of this, I should almost be thinking of, if I call that curve, I called that curve S, right? It's really the partial of S mu partial sigma, because sigma is the parameter of this curve. This curve is parameterized by sigma, so it's called S mu of sigma. So with that in mind, you can actually think of this x as partial S mu partial sigma, and then we're interested in getting so this function here is changing, but this is a derivative, not an increment. You actually need sort of a delta sigma here, right? A certain amount of incremental movement of sigma, And then this will give you ds mu d sigma. Actually, so if I'm going to put x up there, what I really should be doing is sticking with my notation, right? Otherwise, this doesn't make sense, right? This has to be x mu, where now I'm considering x mu as a function of sigma. So this curve here is really given as x mu of sigma. We have to understand that we're now talking about the curve is being named x mu. I guess we're kind of forced into that once we took this derivative. We kind of set the name up. I guess I could have made this an s, and then that would have been an s. But I think it's a little clearer if it's an x, because in the end, that's the more standard notation, right? Is to have coordinates named x. So there's this little sigma here, and then there's another term in the Taylor expansion, and that's the second order term right here, where we now have this increment in the parameter squared. So that's why it's the second order term, and you have this double partial of f. So that tells us sort of the value of the function at p1, but notice it's now all in terms of p0, right? It starts at fp0. This derivative is taken and is evaluated. Let's see, f is a function on the spacetime. The derivative will also be a function on the spacetime. Therefore, it needs to be evaluated on the spacetime, and you evaluate it at p0, and you know that because I didn't put an argument there. Likewise, this curve here is, now this is a derivative of the curve with respect to theta, and that derivative has to be multiplied by some increment of theta. This is the part that's kind of missing from the Meissner, Thorne, and Wheeler analysis, this partial theta. What he does is he ultimately calls point that is going to be at theta equals 1. So this term sort of like disappears. He always has the increment value of P1 is at 1. I felt that was a little confusing myself, but so I'm going to put the theta in there. And then likewise, this is the second derivative. It's evaluated at P0. So everything's local to P0. Then the next thing we do, ignore this for 1 second, is this here, right? We've already determined that since we know that this curve, the curve we're talking about, that moved from P0 to P1, that was a congruence of as a member of the congruence given by x. So this guy here, right, or this guy here, both, they become just x mu. And this is x delta. And this is x mu, right? So that's how these congruences get into these Taylor expansions, by the definition of the fact that this curve is, by definition, the curve by which x is the vector field that is always tangent to the curve, and that's what this means by the definition of tangency, as I showed in just a moment ago. That's sort of why I reviewed this. Now you can understand why we would put that in there. What's missing now is this little delta increment. Oh, that should be a square right there. So then we can do the same thing for P4, right? We write exactly the same expression as this, but now P4 is the value at P1, and the direction is going to be along this curve here, whose tangent vectors are y, and that curve I've decided to call its parameter lambda. And so, but it starts at P1, so now I need the argument to remind us that everything here starts at P1. Oops, I even forgot one right here. There should be one right here telling me that that second derivative is evaluated at P1. So I can calculate the value at P4 this way, right? And likewise, I can do the exact same thing with P3, starting along the y vector field first, and then moving along the curve that's controlled by the x vector field second, and I can get a value for f of P3. And then I can ultimately take this difference, right? So how do I calculate this FP4? Well, I've already got FP1, all in terms of F0. It's an approximation, but it's to second order. So I can stick that there. I can take this guy here, and I can take its first derivative with respect to alpha. which would give me something like an f alpha here. Then I would get a partial x alpha there. Then I would get another term, because this would be a product rule, right? So I would get an x mu partial alpha f alpha, right? So you can imagine taking the derivative of this using the product rule, and you substitute that derivative into here, and then you can see you could take the second derivative of that thing and you could substitute it into there. And then what you do is you get rid of all of everything higher than second order you get rid of. So you start culling terms that are just too high orders, where you end up with some cube combination of delta parameters, right? Either delta sigma, delta lambda, delta sigma squared, delta lambda squared, right? That would be a fourth order term. If you had delta sigma squared, delta lambda, that'd be a third order term. If you had delta sigma, delta lambda, that'd be okay. That's a second order term. So you get rid of all the higher order terms. And so when you do this, what are you left with? Let's go ahead and do this for FP4. Instead of just waving my hand, I might as well just do it. So here's what we have for the expression for FP1. Now I'm going to sort of the condensed notation where I have this single line alpha, right? F alpha is defined as partial f partial x alpha, just like that. So in order to make this substitution, the first part is easy. I just take this whole thing, there's no prime there. I take this whole thing and just substitute it right in there, right? So that's easy. This part, I actually need to take f and calculate the derivative of f with respect to alpha. The derivative of f at P1. Notice everything's at P1 here. So I need to take the derivative of f and evaluate it at P1. Well, this is FP1 here. So the derivative of this guy with respect to alpha will then get substituted right there. So let's do that. So the first thing I'll do is I'll subtract P1 from both sides to create this difference. And that ultimately will allow us to get quickly at what we're after, which is the difference in these 2 points. It's a way of ultimately getting things to cancel out conveniently, but we want to address the interesting. This, by the way, is just simply substituting that, so that's easy. But this is the one that we want to have a quick look at. We're trying to understand the value of the derivative, the ordinary derivative with respect to of f, with respect to the coordinates, times the value of the vector field y at P1. But we need to convert this to local, to facts that are, to numbers and derivatives that are local to P0, right? So we want to get everything local to P0. So the way we do that is we make it's a Taylor expansion for this full function, this combined function, f at P1, y of P1, that product. We're going to Taylor expand that guy from P0 to P1. And that expansion looks like this, where we take the value of that combined function at P0, and we add to it that function's derivative with respect to beta times the gradient vector beta multiplied by the same delta, not delta lambda in this case. In this case, it's delta sigma, right? Delta sigma. And the reason is we're starting from P0. Sigma is the parameter of this x vector field's curve. So we're moving a delta sigma up to point P1. And what we're evaluating is we want to know what is f alpha y alpha, which is a function at P0. We want to know what is the value of f alpha y alpha at P1. And we just Taylor expand it. So we need to take this guy's derivative to first order and multiply it by some increment delta to get this change. And that's what this is here. And so this notation is actually pretty cool. Right, I'll just blow it up a little bit. This is the function. We're taking its derivative with respect to the coordinates using the beta index. So we put the line outside the parentheses. So you've just got to think of this as, if we just rename that function g, this would be g beta, right? So that's the kind of thinking we need to put in play here. for the purposes of the notation. Now this last term here, it's already second order. So any first order approximation or second order approximation is just going to make it third order or higher. So we just take this thing wholesale down below, and because we could repeat this analysis, what we just did here, we could repeat it for this function, right? But we're already carrying around a delta. In fact, there should be a delta in here, right? That's important to remember. There's a little delta lambda that's part of this function that needs to be here. It's not going to contribute much to the derivative, but it does need to be there. Actually, that delta lambda should be inside. Okay, I put them all back in where they belong, right? This delta lambda belongs in here. That's all part of the first order piece. Then that we're taking the derivative of that first order piece, which includes the delta lambda with respect to beta, x beta, but then you need this delta sigma to really convert this x beta into an increment along the curve. I'm kind of complicating things because I'm trying to track the parameter change along the curve, which Wheeler didn't do in his book. He just sort of set it equal to 1. I thought that was quite confusing. So now I'm adding it in, and of course as I add it in, I kind of realize why he left it out, because you've got to carry around all these little delta terms. But they're actually pretty convenient too, because they unambiguously tell you what the order of the terms are. So for example, you can see right away that this thing here, given that this is a constant and this is a constant, it's going to be delta sigma, delta lambda. So you know this is a second order term. And you can right away say that any operation on this that involves taking a derivative or adding a new vector field piece to it is going to make this a third order term. And so the only resulting piece that could possibly matter here is the 0th order approximation to this guy, which is simply the value of this thing at p0. So you're kind of saying that this second order derivative, this second derivative piece here in that Taylor expansion, we're just going to set it equal to its value at p0. And as such, now you have the difference between fp4 and fp1. It's this thing right here. Now, this guy gets expanded. And let's expand. This is simple. It's all straightforward. That's simple. But this one here we can expand because it's a derivative of a product. And that's a function on spacetime, and that's a function on spacetime. So there's a product rule expansion available to us for this piece. So let's work on that. And that expansion of just this piece, just this parenthetical piece here, is this guy, right? So this is a derivative with respect to beta. So we take the derivative with respect to beta of the first piece of the first factor, multiply it by what's left over. And then the second factor, multiply it by what's left over. And of course, we could use this third factor, but it's a constant, so that last term would be 0. And so this now, although there's a second derivative here, it's still only this expansion is first order, but when you substitute it back here, you pick up this delta sigma, so you end up with, you have an x beta delta sigma here, so you end up with an x beta delta sigma there, and an x beta delta sigma here. So you have a product of two increments, which means these are both ultimately second order. So you'll keep those, but you'll throw out the rest. So anyway, we've constructed fp4 minus fp1. Likewise, you construct fp3 minus fp2. And then you construct very quickly fp1 minus fp0 and fp2 minus fp0, right? Those are easy to construct because fp1 minus fp0 is just this minus that, which is all of this. And you have the same kind of construction for fp2, where essentially the x's are replaced by y's, because fp2 is, well, hold on. Because fp2 is just moving along the y direction first using the lambda parameter, whereas fp1 comes from moving along the x confluence of curves using the sigma parameter. So you can basically just change the x's to y's and the sigmas to lambdas, and you can create fp2. And then this, what you do is you rearrange this a little bit, like so, and you get the difference fp1 minus f. So you create fp1 minus f, fp2 minus f, fp4 minus fp1, fp3 minus fp2, and fp4 minus fp1 is going to be something that looks like this, with this little piece here substituted for that. And fp3 minus fp2 is going to look very similar, except again, the y's exchange for the x's, and the delta lambdas exchange for the delta sigmas, and vice versa. And then you subtract everything, and you throw away all the higher order terms, anything higher order than second order. And what do you finally end up when you do that? And this is what you get. The difference between fp4 and fp3, which is what we're after, is this string of differences, p4 minus p1 plus p1 minus p0 minus p3 minus p2, fp2 minus p0. And if you check all this out, it just arithmetically cancels straight up. But what's nice is it helps us, it simplifies all of this algebra a lot, because you end up, you know, we have these differences. We've calculated these differences in as raw form as we can. But the only the upshot is the only term that survives is in fact this one interesting term here. Everything else is going to either strictly cancel, it'll turn out, or it will die the horrible death of the third order. So this is the only guy that survives, but it survives because the y and the x are interchanged and the lambda and the sigma are interchanged. And so that's the only term that actually makes it out of this thing alive. And when you break that guy down, what do you get? Well, you break that, we've already done it. We've broken it down like this. So let's make that substitution and see what survives between that difference. Whoops, I just noticed that this has to be an x in here. This is x alpha. And so that difference now is, you blow this up, just like we did, and you get this guy, and you blow this up, and you get this guy. But this and this are actually the same, because the second partial derivative of any function, x alpha, x beta, x beta, it's true that these partial derivatives commute. So, so I can change this one to f. I can rename the dummy indices to f. Let's see, f. This has to be. Wait a minute. Hold on. I want to rename these indices here. I would go f. I would say beta alpha. See that they commute. So f beta alpha equals f alpha beta. So that's no big deal. And then I say y beta x alpha, and then I just rename the dummy indices. I rename f beta alpha and alpha alpha to beta, and I get f alpha y alpha f beta x beta, and now this is exactly the same as that, and they cancel. So the fact that ordinary partial derivatives, well, partial derivatives like that commute, means those terms go away. So the only thing that survives are these two terms. And those two terms look like, oh, and I pulled out the two linear increments out front, just show everything here is second order now. So now I rewrite this expression. I'll just break it down to dissect it, but it's the same for this expression too. They're both structured the same. Again, exchanging x and y's is really all you have to do. So this term here is defined by this. It's the partial derivative of f with respect to x alpha. This is the partial derivative of y with respect to x beta. Again, you have to remember y is a vector field. It's a function on the spacetime. So this derivative, if you're given that vector field, this is an unambiguous derivative. And then x beta is just x beta. So now we rearrange this a little bit to be suggestive. And this is... I take the x beta, move it to the front. take this derivative, take this term here, move it to this side. That's what this is. This piece here is the partial derivative of f with respect to x alpha. And then we have this derivative operator acting on this guy. And now it's pretty straightforward to see this is, in our coordinate free notation, the vector x. This is the vector y. And this whole thing can be written as x, y, which are vector fields, acting on an arbitrary vector x. And likewise, if you calculate this guy, you're going to get yx operating on a vector x, and therefore this whole thing is the commutator of x and y operating on a vector x, which is what we were intending to show. We kind of knew where this was going to end, but now we understand that this difference, the difference in the function value of P4 and P3, can be understood in terms of the commutator of x and y. So that's the curved spacetime approach, where now in the Wheeler version of things, when you get to the end, remember I've kind of moved a little quickly here, but I still have these two guys floating around. In the Wheeler versions of things, they set them both equal to 1, right? So, and that's fine. That's we can do that, right? That doesn't affect our definition at all. But I like keeping them around just because I kind of like understanding this in arbitrary terms, because ultimately you would have to have a delta sigma delta lambda here. So that would basically say that the difference in those two values is x and y acting on the function multiplied by these little increment factors. If you set the little increment factors to 1, then that is the difference. Okay, so one of the reasons this is important has to do with our understanding of coordinate systems. If we were to look at this as an opportunity, we're given an opportunity, let's just consider 2 dimensions, where we have 2 vector fields. And look what it does. This is pretty convenient, right? The vector fields break up space-time into these curves. So if I have 2 of these curves, I'll make a nice green one here. These curves will intersect, and because of the nature of the way these vector fields work, at least in certain regions, this point P2 is the intersection of only 2 curves. So if I knew the parameterization lambda, and all of these green curves are going to be parameterized by the same lambda, right? So when I pick one value of lambda, there's a point on that curve, that curve, that curve, that curve, that curve, that makes up this lambda. Likewise for sigma, right? There's a point on this curve, this curve, this curve, this curve that all have the same value of sigma. It seems like, well, I could take a point in space-time, and if I knew where it was on the y vector field's congruence, and if I knew what that parameter value was, and if I knew the parameter value on the x confluence, then I could have a coordinate system based on these 2 vector fields. So if I have 2 vector fields, it seems like I could lay down a coordinate system based on the idea of the parameters that build the curves of these vector fields. So, but this problem that we have, that we just demonstrated, that P4 and P3 are not the same points, despite the fact that the construction has us moving delta sigma in this direction and delta lambda in this direction, and likewise delta lambda in this direction and delta sigma in this direction. That means this point P3, it's a sigma curve. Let's imagine that this point is on the 0, 0 sigma curve, but this one is on this point P3, it's on the curve delta delta sigma, and this point P4 is also on the curve delta lambda delta sigma. You got to keep it in the same order, right? Delta lambda delta sigma. So the problem is we have, for this vector field, we have 2 points that have the same parameter values on through these two vector fields. In other words, if I tried to lay down a coordinate system using the curves associated with these two particular vector fields, I'm going to have points that are not the same point but have the same coordinates if I'm using the parameterization of these curves. And that's no good, right? That's not going to work. So this is an important fact because we want to know if every vector field that I give you, if we could make a coordinate system out of those two vector fields. And clearly the only way to do that is function values at points that are arrived through two different orderings of two different directions, like we did in this case. Function values of those points have got to be the same because it's got to be the same point. And the only way that'll happen is if the commutator of the two vector fields is 0. And so if the two vector fields have a commutator that equals 0 everywhere, because remember, these are functions of spacetime. So this is the commutator of x as a function of spacetime with y as a function of spacetime. That commutator, if that equals 0 everywhere, then you can actually create a coordinate system. You can find a coordinate system where the x basis vectors, or the basis vectors, are partial alpha, partial alpha, right? We can just write it as, we can find a coordinate system x mu where basis vectors can be given as partial derivatives from that coordinate system. That's what a coordinate basis is. But not every vector field, not every basis for a vector field throughout spacetime can actually be written in terms of a coordinate basis, and it has to do with the commutator not equaling 0. I guess the better way of saying it is in terms of the coordinate basis at these points. And you know, this topic is to do with this is basically an important element of the idea of non-holonomic and holonomic bases, or rather non-holonomic and holonomic coordinates. And we'll probably talk about that later, especially when we talk about the tetrad formalism. But the point being is that, well, first of all, again, we've got some intuition about the commutator. We've understand how to do it in curved spacetime. That was today's mission. But what we've also, our understanding is, we can kind of see, we can kind of see how these commutators are telling us whether or not vector fields themselves can be bases of vector spaces that are located at each point. So the question I might ask is, at this point P0, right, I have a vector space V. Well, what's the basis? Well, I want the basis of this vector space, which here is, say, two-dimensional, to be x at P0 and y at P0. I want that to be the basis of this vector space. And that's perfectly fine as long as x at P0 and y at P0, right? I'm now going to combine them, you know, at this point. I'm going to merge them into the single vector space at that point. And that's okay to do. The question is, can I ever find a coordinate system where this guy is essentially phi mu, and that would be phi, say, 0, and this guy would be phi 1. Can I ever find a coordinate system that will do that? It'll take those two vectors and convert it into a phi 0 and a phi 1 just by changing the coordinate system out here. And that's what you may or may not be able to do depending on whether the commutator of those two vector fields is 0 or not. We'll talk about that more in the future. But mission accomplished. We've covered the commutator in curved spacetime, and now we're going to get back into the curvature tensor a little more. Okay, see you next time.